Hello, here's another couple of capacitor questions. We're starting here. Capacitance is measured in farads. Define the farad. Right, because we're just talking about the unit here, we can put it in fairly stark terms. A bit like when we're talking about a volt being a joule per coulomb. A farad is a coulomb per volt. So coulomb per volt. Figure 1.1 shows the graph of potential difference against charge Q stored for a capacitor of capacitance C. State the quantity represented by the gradient of the graph. So gradient V over Q, so that's 1 over the capacitance. Then area under the graph, so a half QV, that is equal to energy. Part C, you are given 3 capacitors of capacitances, if I can say it, 100, 200, 500 microfarads. Calculate the minimum total capacitance of these in combination. Show how the capacitors are connected. Right, well, you're going to get a minimum with capacitors when they're all in series. The same as you get a minimum resistance when resistors are in parallel. So what is the minimum going to be on this? Well, our common denominator will be 1,000. So we're going to have 10 over 1,000, 5, and then 2. So 17. So we want 1,000 over 17 microfarads is going to be our minimum resistance. So what does that come out as? That is 58.8. microfarads, so 59 microfarads to 2 significant figures. Right, that was that one. Part D, 0.1 farad capacitor. Right, that's quite a beast of a capacitor. Charged at a constant rate, steady current of 40 milliamps for a time of 60 seconds. Calculate the final charge stored on the capacitor. Right, so they're keeping a steady current, so that's unusual, I suppose, in some ways for charging up the capacitor. But the charge stored is going to be the current times the time. So that is 40 milliamps, so 40 times 10 to the minus 3, multiplied by 60 seconds. So that is going to be 2,400 divided by 1,000, so that's 2.4 coulombs. Energy stored. So energy is what have we got? We've got charge and we've got capacitance. So we're going to want to use that one, that variant of the formula. So a half Q squared over C. So 2.4 squared, because that's our stored charge, divided by 2 times 0.1. So 0.2. That is equal to 12 times 2.4 if we divide one of the 2.4s by 0.2, which is what, 24 plus 4.8, which is 28.8 joules, which is 29 joules to our usual 2 significant figures. Right, that was a nice warm-up one, unless there's more to the question. Nope, there isn't. Right, okay. Define capacitance. Right, so this is now contextualized compared to where we were doing the farad before. Farad's quite stark. Capacitance, we want to give a bit more maybe depth, flesh it out a little bit. So capacitance is the charge stored per unit potential difference. Unit potential difference. So these are things, we can see we're talking about the same things here. We're still talking about coulomb per volt, but now because we're talking about an actual thing which has got some capacitance, we're talking about the charge stored rather than just coulombs, and we're talking about the potential difference across the thing which has capacitance rather than just talking about volts. So, sort of same, only different when you're making a distinction between farads and capacitance. Part B, figure 2.1 shows 2 capacitors of those capacitances connected in series with that battery. Right, everything's in the picture. Right, calculate the potential difference across the 150 microfarad capacitor. Right, so we've got the same charge is going to be stored on both of these. Yeah, these will get charged up. So we'll have Q is the same for both capacitors. So that's our sort of starting point with dealing with all of this. So that means we're going to have C times V for each one. Therefore, C times V is the same. So therefore, the 150 microfarad capacitor has 3 times the voltage of the 450 microfarad capacitor. So they can end up having the same CV and therefore the same Q. So that means we're going to have 4.5 volts across the 150 microfarad capacitor and then the other 1.5 over the other one. So what is the charge stored in that 150 microfarad capacitor? So our charge stored is the capacitance multiplied by the voltage. So that's 150 times 10 to the minus 6 multiplied by 4.5. So that means we've got 1.5. Let's write that out again. 1.5 multiplied by 4.5 multiplied by 10 to the minus 4. 1.5 4.5 is 6 3/4. So 6.75 times 10 to the minus 4 coulombs. 6.8 times 10 to the minus 4 coulombs. Two significant figures. So that's our charge stored. What's the total capacitance of the circuit? Okay, right, they're not asking for much there. So we've got, 450 is going to be our denominator. So we're going to have that divided by 4. 450 divided by 4, which is equal to 112.5 microfarads. So 110 microfarads. Two significant figures. It's quite a. At least I like it when they give us nice numbers for doing the calculations. I think we've got a bit more. We do have a bit more, right? Fully charged capacitors, shown in B, are disconnected from the battery. They're then connected in series with a resistor, resistance of 45 kilo ohms. Right, okay, that is a resistor. And the switch is open, right? PD across the capacitors is measured with a voltmeter of infinite resistance, right? Measurements of V are made at regular time intervals. Show that the time constant for the circuit is about 5 seconds. Right, okay, so our time constant is equal to C times R. C for these two, well, we just worked it out on the last bit. It was 112.5 times 10 to the minus 6. And then we need to multiply that by 45,000. So multiplied by 4,5, times 10 to the 3. Right, that's what we're going to get on that then. So we've got, that's going to be a 10 to the minus 3. Let's just go through these in bits. We're going to have 4,500. That's multiplying it by 100. Then we're going to have another 450 plus 90 plus 22.5. So that's going to be 562.5 multiplied by 10 to the minus 3. So that is 5062.5 times 10 to the minus 3, which is 5.0625 seconds, which is roughly 5 seconds. So showing that. On figure 2.3, sketch the variation of PdV with time. Right, okay, so we need to get our, at 5 seconds, which is our time constant. We've started at 6 volts. We had that. That was our starting point, wasn't it? Pretty sure that's what we had, wasn't it? 6 volts. Let's go back to 6 volts is what we're starting at. So we've got to go through there. Our time constant, then, it would have dropped down to about 2.2 or something. So we're going to have to go through there. and then we're going to have to drop down to a third of that just above. So let's say around about here, around about here, around about here. So each time constant, we're dropping down by the same amount, and then try and join them up in that fashion. It's actually pretty good for me. Right, but yeah, you're going to want to actually have those values marked on there, because otherwise, they've given us labels here. We've got numbers on both axes, and we have done these calculations. So make sure you're cutting through the right points. Otherwise, you're not going to get the marks. At time t equals 0, calculate the ratio energy stored by the small capacitor divided by energy stored on the big capacitor. Right, so we're going to have, well, energy is a half Q squared over C. Now they've got the same charge on them, so that's all going to cancel off. And the halves are going to cancel. So the only thing that's going to be left is the capacitance. So we've got 1 over 150 divided by 1 over 450, because we can cancel the microfarads as well. So that's going to end up being 3. That's the ratio that we've got there. We're going to have more energy on the smaller capacitor because it's harder to push the charge on. If you've got a larger capacitance, okay, you can store more charge on it. We can store more charge on this 450 microfarad capacitor, but if it's got the same amount of charge as this one, we've had to do more work to fill up the small one. Final part, state and explain how the ratio varies with time. Well, we can see that this calculation that we've got here isn't going to change, because this Q, they're always going to have the same amount of charge on the capacitor. When we're discharging it, the electrons are going to be leaving at the same rate from both capacitors. So Q always stays equal for both of them, in which case we're always going to have this same ratio. So the ratio will not change with time, because the Q is always the same, because Q remains equal for both capacitors. Remains equal for both capacitors. Yeah, that's the thing with the way that they're discharging, because we got them in series, they're always going to have that equal charge on them. Yeah, that was a nice question, that one. It was got a bit more involved with some of the descriptions and the graph plotting. So there you go, another couple of capacitor questions.